Alright, hello everyone. Hope you guys are doing good. So, finally, my college exams are over, which means I am back at practicing competitive programming and making these solution videos as well as some other kinds of videos that I have planned for this channel, right? So, yeah, I hope you guys are doing good. And today I'm going to be discussing the solutions to Codeforces Round 783. It was a Div-1 and Div-2 parallel round which was held yesterday, and I'm going to be discussing the first 4 problems from the Division 2 round, right? So yeah, talking about the round, I think it was a pretty neat round, with the first few problems being pretty much the same as they should be, but there was kind of a large difficulty gap between C and D. But overall, I'd say there was like this round was well balanced, and I don't have any complaints, right? So yeah, a neat round. And without any further ado, let's start with the solution to problem A. So in this problem, we have a grid with n rows and m columns. We are basically allowed to move in any direction, that is left, right, top and bottom, in one move, right? So that's the thing that we're allowed to do, but there is this restriction that we cannot make the same move twice in a row. That is, we can't go right twice in a row, we can't go left twice in a row, and same goes for top and down, right? So yeah, that's the restriction that we have, and we basically need to tell what is the minimum number of moves in which we can reach from 1 comma 1 to n comma m, right? So initially we are at 1 comma 1, finally we want to reach at n comma m. So what is the minimum number of moves, provided that we don't make the same move twice in a row? So yeah, that's the problem. Sorry. And let's now have a look at the solution. So there is not a lot to talk about in this problem. Basically what you have to do here is at every step try to make the greedily best choice that you have, and obviously that's going to be the right decision, right? So that is going to lead to a solution with the minimum number of steps. So let's say initially we are here and we try to make the greedily best possible choice. So this is a 5 cross 10, this is a 10 cross 5 grid actually, and we try to make the best possible decisions and then we reach here. But now the problem is that we need to go down 5 times, but to do that we can't just do 5 down moves, because that is not allowed. We can't have more than one down move twice in a row, right? So now what we'll do is we'll go down, and now we can't go down again, so we'll go left, and then now we can go down, and then we go right, now we can go down, then we go left, then down, then right, and then down. And this is obviously optimal because at every point of time we are choosing the best possible thing that we can do, right? So this will give us the minimum number of steps that is needed, right? So yeah, that's pretty much it. That is the entire solution. Let's just form a mathematical formula for it. So we have an n cross m grid, and let's just assume that n is greater than or equals to m. If that's not the case, then we can basically swap n and m, because everything is uniform. We just are interested in the values of n and m, and we don't need to differentiate between what is n and what is m. So if n is less than m, we can simply swap n and m. So we can always guarantee that n is greater than or equal to m. Alright, so one case that we need to get rid of is when the answer will not exist. So they have also said that if the answer doesn't exist, we need to print -1. Now how do we take care of that? So it looks like an answer always exists because it is always possible to reach from 1 comma 1 to n comma m this way, right? But it turns out that if m is equal to 1, that is there is only one column, then basically there is this one column and there are a lot of rows, so we just need to go down, right? So in that case, if n is greater than or equals to 3, then answer will not exist. And the reason for that is simple, because to reach from 1 comma 1 to 3 comma 1, we basically need 2 down moves in a row, and nothing else can make us reach from 1 comma 1 to 3 comma 1. But 2 down moves in a row is not allowed, right? So if m is equal to 1 and n is greater than or equals to 3, then the answer will not exist for sure. And now we just need to find a mathematical formula which describes this path, right? So essentially what we are doing is, first of all, we are making 2 into m minus 1 moves to reach from this point. So we are making 2 into m minus 1 moves to reach from this point to this point, right? M minus 1 down moves and m minus 1 right moves. So number of moves. First we are making 2 into m minus 1 moves. and now we have successfully reached here. Okay, so now we are making, in every 2 moves we are getting down by 1 position, right? Okay, so now let's say remaining number of down moves that we need to do is n minus m, right? So this is the remaining number of down moves that we need to have. And now if remaining is odd, then you can clearly see that in every 2 moves you are making 1 down move, but you are starting with a down move, right? So if remaining is odd, then the total number of moves that we'll get is 2 into remaining minus 1. Else the number of moves that we'll get is simply 2 into remaining, right? So that's it. So the total number of moves will be 2 into m minus 1, plus if remaining is odd, then 2 into remaining minus 1, else 2 into remaining. And that is it. That's the entire solution. Alright, so this completes the solution to problem A. There is no need to have a look at the code here because it's just a simple mathematical formula. So now let's move on to the next problem, problem B. Okay, so this one is an interesting problem. So there are m chairs which are arranged in a circle sequentially, and the chairs are numbered from 0 to m minus 1. And there are n people who want to sit in these chairs, and the ith person wants at least ai empty chairs both on his left as well as right side, right? So what is happening here is that if the ith person is sitting on the jth chair, then ai chairs to the left of the jth chair as well as ai chairs to the right of the jth chairs, all of them have to be empty. So there is there can't be any person sitting in these chairs which are at a distance less than equal to ai from the jth chair, either to the left or to the right. Here left and right are given according to the condition that the person is facing towards the center, right? Obviously. Okay, so we just need to tell whether or not it's possible to sit or to make all the persons sit in a particular seat and satisfy all the conditions at the same time, right? Yeah, so we just need to output yes or no. We need to output yes if it is possible to make all the n persons sit in the circle such that all of their n conditions are satisfied. That's it. So let's see how we can solve this problem. I have a really bad throat, so I request you all to please excuse me for that. I'll be coughing in between. Anyways, so let's see what we have here. So this is a circular table that we have, right? And there are people sitting in some chairs. There are n people sitting in the chairs, and in between them there are these empty chairs. Okay, so this is the situation that we have. So this is the first person, this is the last person, let's say. This is the second person, this is the third person, and this is the n minus 1th person, so on and so forth, right? You get the idea. Okay, so now let's see what's going on. So in order to satisfy all the conditions, what we need to have is, in this region, the number of empty seats should be greater than or equals to a of p1, and they should also be greater than or equals to a of p2. So the number of empty seats here should be greater than or equal to nothing but max of a of p1 and a of p2. Okay, so that's pretty obvious to understand. Similarly, the number of empty seats here should be greater than or equals to max of a of p2 and a of p3, so on and so forth for every situation, right? So the number of the total number of seats, total number of chairs that we will get is, first of all, we will need n chairs to sit all the n people. That is pretty obvious. And now let's talk about the empty chairs. So the number of empty chairs here is max of a of p1, a of p2. And then we'll have max of a of p2, a of p3. And finally we'll get max of a of pn and a of p1, right? So now our job is to find this permutation p1, p2 up till pn, which minimizes this value. And finally we'll just find this minimum value and check if this minimum value is less than or equal to m or not, because at the end of the day we have m chairs, right? And if it is less than or equal to m, then the answer is going to be yes, otherwise the answer will be no. All right. Right. So let's see how we can find the permutation which will minimize our values. So first of all, what we'll do is we'll sort the array A. So sort A, that is A1 is less than equals to A2 less than equals to A3 less than equals to n. We are obviously allowed to do that because all these A values are simply random. So let's say we have sorted A. Okay, and now let's see what's going on. So if we look closely at this expression, every element is coming in this expression twice. We can see that P1 is coming twice here, in the first term as well as in the last term. Similarly, P2 is coming in the first term and the second term. So similarly, similarly we can see that every person is coming exactly 2 times, right? Okay, so now let's try to find out the contribution of every person. Okay. All right, so let's look at the contribution of every person. So let's look at person number n. So notice that I have already sorted the array. So an is the largest value. So let's look at the contribution of an. Okay, so it doesn't matter which two people are sitting adjacent to the nth person. The value an will be the value an will be strictly greater than the values of its neighbors, right? So the contribution of an is always going to be 2. Okay. All right. Now let's look at an minus 1. So now let's look at a of n minus 1. So let's say we have this person. Let's say this person is the nth person and he is sitting here. It doesn't matter where we seat the n person, where we seat the nth person, because its contribution is always going to be 2. Now let's look at n minus 1. Now notice that we need to minimize our final sum. So we need to have the minimum contribution of the people who have higher values, right? So we need to minimize this contribution of an minus 1. But notice that there is only one person who is greater than an minus 1, and that is an. So we can't reduce the contribution of an minus 1 by more than 1, and we can have its contribution to be equal to 1 if we seat an and an minus 1 together. So its contribution is 1 if we seat an and an minus 1 together. Okay, so what we'll do is we'll say that this person is nothing but an minus 1. N minus 1. Okay, and now both of them are sitting together, so we can say that both these positions are fixed. So let's assume that this is just one person, not two people. Okay, and now let's look at a of n minus 3, n minus 2. So again what we have is we have just one person which is greater than a of n minus 2, and that person is this combination of an and an minus 1. Now obviously these are two people, but they will be considered just one person because their position is fixed now and they are sitting adjacent to each other. So we can merge them to be one person. So now what we can do is the contribution of an minus 2 will be 1 if we seat an minus 2 adjacent to an minus 1. Okay, so we can say that this person will now be n minus 2. So now we can just keep on doing this, and what we'll get is we have to sort the array and then we just have to place all the elements together, and that will give us our final best answer. Okay, so I have proved here why this is working, because we need to minimize the contributions, and this is the way we get minimum contributions. Okay, so the optimal arrangement will look like n minus 1, n minus 2, n minus 3 up till 1, right? So that is the optimal arrangement that we have. So this proves what the seating arrangement will look like, and to get this final answer, it's now pretty easy. So the minimum number of seats that will be required is n, plus max of AP1, AP2. AP1 is just A1 and AP2 is just A2. So max of them will be A2. So it will be A2 plus A3 plus up till AN plus AN, right? So the contribution of AN will be 2 and the contribution of everything else will just be 1. So it will be A2 plus A3 plus up till 2AN plus N. So if this value is less than equals to M, then answer will be yes, otherwise answer will be no. So that completes the entire solution. Let's just have a look at the code. So the code is pretty simple. We just take in the array, we sort it, and then we sum up all these values from A2 to AN, and then we add AN again. So we have our expression. So if this expression is less than equal to M, then the answer will be yes, otherwise the answer will be no. All right. So yeah, this completes the solution to problem B. Now let's move on to the next problem that we'll be talking about, problem C. So this one, I personally thought this one was a bit easier. Like it was a bit easier than even problem B according to me. So let's see what this has to say. So we are given an array A consisting of n positive integers, and we also have an array B of length n. Initially all the elements of B are equal to 0, and in one move what we can do is we can choose an integer I, and we can either add AI to BI or we can subtract AI from BI, right? So these are the moves that we are allowed to do. We need to tell what is the minimum number of moves needed to make B increasing, right? So yeah, that's the problem. Okay, so let's see how we can solve this. There is just very simple, easy observation, one observation required to solve this problem, and let's see what that observation is. The problem is simple. We have an array B which is initially all zeros, and we have an array A, and we can have several moves. In one move we can either add AI to BI or we can subtract AI from BI, and we need to sort this array B in strictly increasing order, and we need to tell the minimum number of moves to do so. Okay. So let's look at one crucial observation. So the final array, the final sorted array will have some negative elements, so these negative elements may be 0 or more, and then some positive, and then some non-negative elements, right? Okay, so this is what the final sorted array will look like, obviously, right? So let's say this is our final array, B1, B2, B3 up till BK, then BK plus 1 up till Bn, right? So let's say these are all the negative elements, and BK plus 1 is the first non-negative element, right? Okay. Now if BK plus 1 is the first, so let's say this is BK plus 2. So let's say that BK plus 1 is the first non-negative element. Now we know that BK plus 1 is strictly less than BK plus 2, right? So BK plus 2 is positive, right? Now what we can have is BK plus 1 should definitely be 0. That's the main observation here. And the reason for that is that initially all the values in B are 0, and if BK plus 1 is not equal to 0, then that means we are doing some extra moves to make it non-zero. But those extra moves are not required, because even if BK plus 1 is equal to 0, the array remains sorted. So there is no need to have any moves done on BK plus 1, right? So BK plus 1 should definitely be 0 in order to have the minimum number of moves. So what that means is that the array should always contain a 0. The final array should always contain a 0. And now once we have made this observation, what we'll do is we'll look at the constraints, and the constraints are small and they allow for an O of n square solution. So then what we can do is we can iterate for the position of the 0. We can iterate for the position of the 0 and for each position find the minimum number of moves, operations. So yeah, this is what we are supposed to do, but there is still one piece in the puzzle which is missing, that how do we find the minimum number of operations? Well, that is again just a very easy greedy stuff that we can do. So what we can do is that let's say that the ith position is fixed to be 0. So ith position is fixed to be 0. So what we'll do is in the I plus 1th position, we will just do one operation and convert it to a of I plus 1. Okay. And then in the I plus second operation, then in the I plus second position, what we'll do is we'll do the minimum number of operations such that b of I plus 1 exceeds b of I plus 2 exceeds b of I plus 1, and so on, right? And similarly, we can do the operations on all the indices which are smaller than I. So this will guarantee that we have the minimum number of operations required, because at each index we are just doing the minimum possible number of operations which are required, right? So this way we can find out the total minimum number of operations by fixing the position of the 0, and we can iterate on the position of the 0. So then we can have a nested loop, and the total time complexity becomes O of n square, right? So that completes the solution. Let's just have a quick look at the code now. All right. So yeah, what I'm doing is, first of all, I'm iterating on the position of the 0. So that position, let's say, is the ith position. So I'm saying b of I is equals to 0. Then for all the positions j which are greater than I am making bj to be greater than bj minus 1 by doing the minimum number of operations, which is this, the difference divided by a of j and ceiling, right? And then for all the positions which are smaller than I, again I am doing the minimum number of operations in order to convert b of j to be smaller than b of j plus 1, right? And finally I am just taking the minimum of all the operations that I get, and that will be my answer, right? Okay, so this completes problem C. Now let's move to the last problem that we'll be discussing today, which is problem D. And this is kind of difficult because it involves some rigorous data structures, but otherwise I won't say that it's like a very difficult problem. It's a bit complicated because my solution uses a lot of different stuff like coordinate compression, segment trees and stuff like that, but at the end of the day I think this problem is around 1900 to 2000 rated difficulty according to me. I don't know what the Codeforces system is going to rate it, but anyways, let's start with the solution. So we have an array A consisting of n integers, and we should divide A into contiguous non-empty subarrays. Of course, there are 2 to the power n minus 1 ways to do that, and let S be the sum of a subarray, and then the value of the subarray from L to R is, if sum is greater than 0, then the value is the length. If sum is equal to 0, then the value is 0, and if the sum is less than 0, then the value is minus 1 into length, right? So that's what the value of the subarray is. So we need to partition the array into several subarrays such that we get the maximum value of the sum of all the subarrays, right? So that is what we have to do. We need to maximize the sum of all the values of the subarray that we partition our array into. So yeah, that's it. That's the problem. Let's see how we can approach it. All right. Let's see. So let's start with a very trivial O of n square solution. So this solution is pretty straightforward. So what we'll do is we'll make use of dynamic programming, and we'll just have a simple 1D DP array where DP of I will be the maximum sum of values of all subarrays by taking into account the first I elements. So naturally the answer is going to be dp of n, right? We are taking into account the first n elements, and we need to find the maximum sum of values of all the subarrays. Okay, now how do we make transitions? So what we'll do is, we will iterate. So let's say we iterate for the variable j, that is the last element of the second last subarray. Obviously the last element of the last subarray is just I, but the last element of the second last subarray will be j. So that means the last subarray is from j plus 1 to I. So in a way we are basically iterating on the length of the last subarray, right, where j will be the last element of the second last subarray, so the length of the last subarray will automatically become I minus j, that is from j plus 1 to I. Okay, so now let's see what we have. So basically what we have is the sum of the subarray is going to be what? It's going to be the sum of all the elements from j plus 1 to I. So let's say we have already computed the prefix sums of the array. So this sum is going to be prefix sum of I minus prefix sum of j, right? So there are a few cases. So we'll make all these three cases that are provided to us in the problem, and we'll see how we can do the transitions. So if p sum of I is minus p sum of j, which is basically the sum of the subarray, that is negative, right? That means p sum of j is greater than p sum of I. In this case, so this is the first case. So in this case what happens is that dp of I is equals to dp of j obviously plus the value of the subarray from j plus 1 to I. Now we already know that the sum of the subarray is negative, which means that its value is going to be the negative of its length. We know the length is I minus j, so the negative of its length becomes j minus I, right? So it is dpj plus j minus I, right? Okay, second case. So the second case is if p sum of I is greater than p sum of j. In this case the sum of the subarray is positive, so what we have is dp of I is equal to dp of j plus I minus j, right? So we can have dp of j minus j plus I, right? Okay, now we also have another case, which is if p sum of I is equal to p sum of j. So if p sum of I is equal to p sum of j, then again we have a simple relation, which is that dp of I is equal to dp of j, right? Okay, so yeah, that's it. These are all the three cases that we have. Alright, now this is obviously a very trivial O of n square dp, because we'll have to have two nested loops in order to iterate for j and I as well. And so this will definitely TLE because the constraints don't allow for an O of n square solution. So we somehow have to optimize this O of n square using some data structures or something like that, and bring down the time complexity from n square to O of n log n. So how do we do that? Well, to do that, what we do is we notice the important things. So the only thing which depends on j in these two expressions is dpj plus j and dpj minus j, right? So if prefix sum of j is greater than prefix sum of I, we are interested in the values dpj plus j, and then we can just subtract I because that is independent of j. And if prefix sum of j is smaller than prefix sum of I, then we are only interested in this value dpj minus j for all j's, right? So yeah, that is what we are supposed to do. So now let's write down all the steps that are required to optimize the solution. How to optimize? Step 1. So step 1 is, so since you notice that the values in the array can be huge, the prefix sums consequently can be huge as well, right? So the prefix sums can be as large as 5 into 10 raised power 14. That is a very huge value. So we want the prefix sums to be small. So what we do is we coordinate compress the prefix sums. So if you don't know what coordinate compression is, I'll just briefly describe it. So basically what we do is These prefix sums can be huge, but at the end of the day we have exactly n values of these prefix sums, and so the number of unique values of prefix sums will be at most n, right? So let's say we have n unique values of prefix sum. So instead of having these huge values of 10 raised to the 9, what we'll do is we will map all these values from 1 to n, and we'll map the smallest value with the value 1, second smallest with the value 2, and the largest value with the value n, right? So in this way we are basically maintaining the order of all the prefix sums. So if prefix sum I minus prefix sum j was positive before, it stays positive. If it was negative before, it stays negative. If it was 0 before, it stays 0. So in this way we are basically maintaining the relative order of all the prefix sums, but at the same time we are making sure that the prefix sums lie only in the range from 1 to n. Okay, so that is what coordinate compression means. So now we have, I will assume that everyone has understood what coordinate compression means. So now we have coordinate compressed the prefix sums from 1 to n. Okay. Right. So now it's very much convenient for us because the prefix sums are smaller. So now what we'll do is, now I would request you to pay attention because this is a very important step. So for every prefix sum s, what we'll do is maintain two values. The max value of dpj plus j as well as dpj minus j for every j such that prefix sum of j is equal to s, right? So basically for every prefix sum s, if we have an index j such that prefix sum of j is equal to s, we will maintain the maximum value of dpj plus j as well as dpj minus j for that prefix sum s, right? So if you didn't understand what I'm trying to say here, just read this statement which I have written. It pretty much sums up what I'm trying to do. So for every prefix sum s, what we are doing is, if at an index j the prefix sum is equal to s, then for that particular prefix sum s, we maximize the value of dpj plus j as well as dpj minus j. That is, we store the maximum value of dpj plus j and dpj minus j. Okay. So now we have these two values. So what we'll do is, now we want to make a transition, right? So we have we are on an index I and we want to make a transition. So so let's look at the third condition first. So this third condition is really easy. So to maintain this third condition, what we can do is we can just maintain a pretty trivial dp array where dp of x is just the maximum dp value for a prefix sum of x, right? So then we can just update the dp of I by dp of prefix sum of I, right? So yeah, that's going to be very easy. So to maintain the third condition, we don't need to do anything fancy. We can just maintain a dp array. So let's write it down. So to maintain third condition, we will maintain dp of s is equal to maximum dp value, maximum dpj for every j such that p sum of j is equal to s, right? So then to maintain the third condition, what we'll do is the dp of I. So let's say this array is dp1. Okay, yeah. So dp of I is basically nothing but dp1 of prefix sum of I, right? That's it. So this third condition is very easy to maintain. Now let's look at the more difficult conditions, which are the second condition and the first condition. So for every j, every prefix sum j which is greater than prefix sum of I, we need this value dpj plus j. Okay, so for every prefix sum in the range prefix sum I plus 1 to n, we need the maximum value of dpj plus j. And similarly, to maintain this second condition, so for every prefix sum in the range, so notice that here we want prefix sum of j to be smaller than prefix sum of I. So the range becomes 1 to prefix sum of I minus 1. Here we need the maximum value of dpj minus j. Okay, so if you notice, both of them are nothing but range queries, right? We have a range and we need the maximum value of dpj plus j in this range. Similarly, we have a range and we need the maximum value of dpj minus j. So these are just range queries, and we can answer these range queries effectively in O of log n using segment trees. You guessed it, right? So now the solution becomes really easy. We just have to maintain two segment trees. In one segment tree, we'll store dpj plus j for every prefix sum, and in second segment tree, we'll store dpj minus j for every prefix sum, and we'll just do two range queries, one from prefix sum plus 1, prefix sum of I plus 1 to n, and one from 1 to prefix sum of I minus 1. So first query will be on the first segment tree, which stores dpj plus j values. Second query will be on the second segment tree, which stores dpj minus j values. And then also for this third condition, we will just maintain a simple array and update these values. So then we will take care of all these three conditions effectively, efficiently in O of log n time. So we have solved this problem in O of log n time, right? One important step to remember is that once we have found the dp value, we also need to update the segment tree, and that can also be done pretty easily. Right, so this completes the solution to the problem. Let's just have a look at the code. If the solution is not yet clear, I am sure that if you look at the code, it will become much more clearer, right? Okay, so this is just the code for a segment tree. I have written down the code for two segment trees separately, although this could be the amount of hard work here could have been reduced using some structs and stuff like that, but anyways, it is what it is. So we have two segment trees, and then let's come to the correct code now. So first of all, what I'm doing is I am trying to coordinate compress these prefix sum values, so that can be done easily using a map. So here I am coordinate compressing all these prefix sum values, right? So once I'm done with that, then I am building my segment trees, and the initial condition is that for prefix sum of 0, the answer is going to be 0. So I am updating both of my segment trees by 0 plus 0 and 0 minus 0, which is just 0, right? And then what I do is, at the ith position, first query is from prefix sum I plus 1 to n, and the second query is from 1 to prefix sum of I minus 1. Okay, so, and if you notice here, in the first query I have to subtract I, in the second query I have to add I, right? So I will take the maximum value of q minus I and q1 plus I, right? And also the third value that I have to take is dp of prefix sum of I. Okay, so I'll take the maximum of all these three values, and then I get cur as the value of dp of I, right? So now I have the final value of dp of I. So now I also have to update the values in my segment tree. So I will just check in the first segment tree if dp of I plus I is greater than the current value of prefix sum of I stored in the segment tree. If that's the case, then I update my segment tree. Similarly, I update my second segment tree if dp of I minus I is smaller than the current value of the prefix sum of I in the second segment tree. And if that is the case, I update my second segment tree. And if I is equals to n, then I have found my answer, right? So yeah, this completes the entire solution to the problem. So yeah, thank you so much for watching. That is all that I had planned for today, and I will see you in the next one.